Okay, so this is example 2. Example 2. And in this example, we have air being pumped into a balloon in the shape of a sphere. And we want to know how fast the radius is changing. So when you're given a problem like this, you want to start by asking yourself, what do you know? What are you given? So I gave you the formula for the volume of a sphere is 4 equals 4/3 pi r cubed. Now I gave it to you this time, but this is one of the formulas that you need to remember because it is no guarantee that I will give this to you on a quiz or a test. So you need to remember this formula. The other thing that you're given is that the volume is increasing at a rate of 100 centimeters cubed per second. Now it's increasing at a rate. That is not the volume. That's how fast the volume of the balloon is changing. Because this represents how fast something is changing, it's a derivative. So this is the derivative of the volume. So dV dt is equal to 100 centimeters cubed per second. Another thing that gave it away was that it was given as a measurement divided by time. That generally indicates a rate. So this is dV dt. This is not the volume. This is dV dt. And you're asked to find how fast is the radius of the balloon changing. So you're not asked to find r, but you're asked to find dr dt. Because again, it's how fast is it changing is what they're asking you to find. How fast is that changing? So you're asked to find dr dt. And we don't care about dr dt always. We only care about dr dt when the diameter is 50 centimeters. Now you have to understand that as air flows into this balloon, the radius is increasing. And it will continue to increase until it pops. But this radius is increasing, so I'm asking you at a particular time, only when the radius is 50, how fast is the radius changing is what I'm asking. I'm sorry, when the diameter is 50, how fast is the radius changing? One of the things we know from geometry, if the diameter is 50, then the radius is 25. Okay? So we're trying to find dr dt. We're given dV dt and this formula. So what I want to do with this formula is I want to take the derivative of it. So taking the derivative of v gives me dV dt is equal to, now remember 4/3 pi is a constant, so I can pull that out, and I'm going to take the derivative of r cubed. Using the power rule, I know that r cubed is 3r squared. Using the change rule or implicit differentiation, I know that the derivative of the radius with respect to time is dr dt. I am solving for dr dt, so all I have to do now is substitute into this formula what I know. I know that dV dt is 100. I know that r is 25, so that's going to give me, r is 25, so it's going to be r squared, so that's 625 dr dt. Please notice that this 3 and this 3 cancel, so I can get rid of that, and now I have 100 is equal to 4 times 625, which I'm not sure what that is, but I'm going to call it 4 pi times 625 dr dt. I'll leave it like this because this is going to make it easier for me to divide. I divide by 4 pi times 625. And I think if my math is correct, that should give me 1 over 25 pi is equal to dr dt. Now remember, the units are important here. This was in centimeters cubed per second, and this was in centimeters squared. So dividing centimeters cubed by centimeters squared should give me centimeters per second. So my answer is 1 over 25 pi. I'm sorry, that pi is in the denominator. Let's do that again. So 1 over 25 pi centimeters per second. And that is DRDT. So we have completed our second example. Please go back, please watch example number 3.